So the interaction between the different components of the climate system involve the exchange of energy, water, momentum and other nutrients. So although the focus of this week's lectures has been primarily on the surface energy balance, it's important to understand that in the context of other important concepts that underpin how our climate system works. As you now have a good understanding of what the latent heat flux is and that it's proportional to the moisture gradient between 2 points, it's also worth noting that it's actually a representation of the evaporation rate between those 2 points as well. And evaporation is the key process that links the surface energy balance to the water cycle as well as the carbon cycle, and we're going to explore that a little further in the next few videos. So what is the hydrological cycle? This schematic provides a very simple characterization of what the hydrological cycle is. It represents the key water reservoirs in our climate system and indicates that mechanisms exist to which water in all of its forms is exchanged between those reservoirs. Here, this schematic illustrates how much water is stored between different parts of the climate system and the amount of water exchange, the flux, between the various components of the climate system. So the cycling of water between the atmosphere, ocean and land is quite important for weather and climate. Surface evaporation, indicated by these green arrows, provides the atmospheric moisture. Once in the atmosphere, water condenses to form clouds, and when the cloud droplets are sufficiently large enough, they fall back down to the surface as precipitation in various forms, including snow and hail in addition to rain, as indicated by these blue arrows. Water vapour formation in the atmosphere releases heat, which is an important source of energy for the formation of different weather phenomena. River discharge into the oceans as well as precipitation help prevent the ocean from becoming saltier, which in turn has consequences for transport within the ocean. Our oceans do cover 70% of our planet and are the main source of water vapour to the atmosphere. However, over land, the transfer of water to the atmosphere can follow more complex pathways and is connected to biological processes and the corresponding land surface characteristics. So let's dig into the land-ocean contrast further. So we'll start over the oceans. Like the surface energy balance, we have a similar concept to look at the water balance at the interface between the surface and the atmosphere. Starting with this horizontal line, let's assume that that represents the interface between the atmosphere and the ocean. And let's also assume that at that interface, water is conserved, so the inputs equal the outputs. As already mentioned, the atmosphere transfers water to the ocean via precipitation P, and water is transferred to the atmosphere via evaporation E. However, from our previous schematic, the total evaporation over the oceans is 436.5 cubic kilometres per year, and there's only 391 cubic kilometres per year returned to the ocean. Because of our conservation constraint, we need to address this imbalance and include water supplied to the oceans from the land via rivers discharge and runoff from non-ocean surfaces like ice sheets, and we'll represent that by this Q term. Together, the P plus Q should equal to E. However, due to the addition of water to the ocean, we also need to account for the change in the storage of water, S. So the water balance of the oceans consists of precipitation equal to the evaporation, minus additional water input supplied by discharge or runoff, plus any change in the water storage. And that's a very simple expression for the surface water balance over the ocean. For the land surface, the picture gets a bit more complicated because we have to consider the biological aspects as well as how we have modified the surface. We can start at the interface between the atmosphere and the land and assume that at that interface water is conserved. We can start with the inputs into the land surface, which include precipitation P and snowfall Sn. That water will infiltrate the soil, so we have a change in the storage term S. When the soil is saturated and no more water can infiltrate the surface, then any further precipitation that falls will flow across the surface as surface runoff, QS, which flows into our rivers, reservoirs, etc. Water in the soil also drains through to the water table, so we also have subsurface runoff and deep drainage, which is represented here as QG. So how is water returned to the atmosphere? Well, here is where it occurs via different pathways and includes the biology. The first is the evaporation of moisture directly from the soil, referred to as the soil evaporation, ES. Because of vegetation, it complicates the narrative. Firstly, vegetation can intercept precipitation and snowfall, and affect how much water infiltrates the soil. And that water that is intercepted by the vegetation can evaporate back into the atmosphere, which we refer to as the interception evaporation, EI. But water uptake by the vegetation through the soil can be lost via transpiration from the leaves, which we refer to as ET. Together we get a surface water balance over the land consisting of the precipitation and snowfall on one side balanced by the soil evaporation plus the transpiration and the interception, as well as any contributions from the surface and subsurface runoff and any change in the storage. So we've seen that the contrast between the oceans and the land is considerable. So let's put that into the perspective of the surface energy balance and the surface water balance. We can make the assumption that over long time scales we have a steady state and can therefore assume that there are no changes in the storage term for the water balance. Over oceans, the net radiation is predominantly balanced by latent heating LE and the surface heat flux G. If we go to a rainforest, the net radiation is approximately balanced by latent heating, and we can use this to estimate the evaporation rate as Rn on LV, the latent heat of vaporization. So the runoff is approximately equal to precipitation minus evaporation as determined by the net radiation Rn. For a woodland, the landscape is considerably drier, so not all the net radiation is transferred back via latent heating, but also sensible heating. And in terms of the water balance, runoff is much smaller than the P minus E relation. For deserts, a lack of water means that most of the net radiation is balanced by sensible heating with limited latent heating, and due to a lack of moisture, runoff approaches zero. Coming back to the surface water balance over the land, the total evaporation consists of soil and vegetation contributions, and because of that, it's dependent on how vegetation behaves, both in terms of leaf size and photosynthetic activity under different ambient climate conditions. To capture the fact that evaporation from the land surface encompasses biological processes, we refer to the total evaporation over land as evapotranspiration. We can represent the evaporation following the formation introduced for the latent heat flux as a function of the moisture gradient between the surface and an arbitrary point in the atmosphere, and divide this gradient by the aerodynamic resistance Ra. We also scale this by a beta term, which represents the soil water content. Essentially, if there is more water available in the soil, more evaporation is possible. If there is less water available, then less evaporation is possible. As it is difficult to measure the humidity at the surface QS, we often use the surface humidity at saturation, which is also a function of the surface temperature, and we denote that by this QSAT and in brackets TS. As mentioned, evapotranspiration can be split into its respective contributions, including the soil evaporation ES, which is a function of the moisture gradient between the soil and the atmosphere, divided by the aerodynamic resistance Ra, and the soil resistance to moisture loss R soil. The transpiration ET is a function of the moisture gradient between the vegetation and the atmosphere, divided by the aerodynamic resistance Ra, and the canopy resistance to moisture loss RC. The interception is the evaporation of water sitting on the vegetation and is proportional to the leaf area index LAI. Estimates of the evapotranspiration are continually updated, however this schematic indicates the relative contribution of each of these processes, with transpiration contributing the most, followed by the soil evaporation and then a smaller contribution from the interception. As mentioned, biological processes play a major role in evapotranspiration. Transpiration is evaporation that occurs inside a leaf and is transported to the atmosphere via the stomata, which are the small apertures on the leaves of vegetation. The leaf resistance includes the stomatal resistance from inside the leaf to the leaf surface and the leaf boundary layer resistance from the leaf surface to the air. So the leaf boundary layer resistance depends on the leaf area as well as the wind speed. The opening and closing of stomata is strongly regulated by the plant, trying to optimize the uptake of carbon during photosynthesis and minimize unnecessary moisture loss from transpiration that occurs simultaneously. So if conditions are ideal, the stomates open to take up CO2 with some moisture losses, but when conditions are not ideal, like when it's too hot and dry, the stomates close to limit moisture losses with consequently less carbon uptake. Under higher CO2 concentrations, the stomates do not have to open as much to take up the same amount of carbon, and therefore it can increase its water use efficiency. So we've seen that the evapotranspiration consists of distinctive contributions where the transpiration is a function of the moisture gradient and two resistance terms. In particular, the canopy resistance RC is inversely related to the canopy conductance GC, which is the integral of the stomatal conductance at the leaf level integrated over the leaf area index to get the resistance for the whole canopy. Note that the stomatal conductance is a function of the photosynthetic active radiation, water stress, temperature, and air humidity. So through the evapotranspiration term, we can link the water cycle to the carbon cycle as done for the surface energy balance through the latent heat flux. The carbon cycle represents the interactions of two superimposed cycles. The first being the geological carbon cycle involving the chemical weathering of rocks over millions of years and the accumulation of carbon in various sinks within the surface. Secondly, the biological carbon cycle involves the cycling of carbon between the atmosphere and both marine and terrestrial organisms through biological processes over shorter timescales of days to decades. This schematic represents the amount of carbon exchange between different components of the climate system that underpin the carbon cycle. Note that it is the anthropogenic activity that has caused a major disruption to this cycle, such that we cannot exclude the impact that this has anymore. Carbon storage is an important regulator of atmospheric CO2 concentrations. Where land cover change and human uses of land greatly affect the biogeochemical cycles, particularly through the burning of fossil fuels to generate energy and land clearing for a variety of purposes.